Hey guys, this is Mark, and I've created something that I'm really excited to share with you guys, and I am uploading it to my GitHub repository here. Well, I did, and I'm going to leave a link to my repository in the description below. You'll see here it has the Java docs, it has the class and Java file, and it has a Word document, an explanation for my sorting algorithm. Now, what's this algorithm we're talking about? Alright, so as you might have seen, I've created a Sudoku sorting algorithm. Now this generates a Sudoku grid, a valid Sudoku grid, 1 through 9, because this equals 9 in my head, 1 through 9 in every box, row, and column, non-repeating. And so that's for you guys who don't know Sudoku. Brief run through. Anyways, I've tried creating a Sudoku sorting grid, like a generator, before. However, I was really dissatisfied with it. It was about a year and a half ago, right? I think, and it would just do brute force. It would just keep picking random values, and then if it got stuck, it would just start over again. And it took somewhere around 4 or 5 seconds to generate one grid. So about a week ago, I started pondering on this while I was on vacation in Arizona, and I decided to give this another try. And when I did, I was driving home from the airport, which I decided to fly out from Baltimore, and I live in New York, so I was driving for 6 hours. And that gave me plenty of time to come up with the algorithm here. And I wanted to show you, right here, you're going to see a grid pop up. Now, the first time that I wanted to test the time, like how fast it was generating a Sudoku grid, I was testing every single iteration. And when I did that, it came back as 0 milliseconds. And I was thinking, surely it's taking up some processing time. So what I had to do was bulk generate. So I picked something arbitrarily. I picked 1,000,000 Sudoku grids, and I timed it. And it took 7 seconds to generate 1,000,000 valid Sudoku grids. For you math guys out there, that's 7 microseconds. I was excited. And you can pause the video and you can take a look at this grid to make sure that it is, in fact, a valid Sudoku grid. 1 through 9 appearing only once every box, row, and column. So anyways, the code is here too. It's not too difficult. There's 3 methods here, 4 if you include the main. But the 3 methods are generate Sudoku grid, or generate grid, print grid, which you saw right there, and is perfect, which returns true if the grid is a valid Sudoku grid. It's windy out there. Things is blowing against my window. Anyways, I'm going to wrap this up. I'm going to show you my thought process behind the algorithms. So what it does is I've created an array, a single one-dimensional array with 81 indices, and I have a smaller array list with integers 1 through 9, and I use the collections.shuffle method to mix it up and insert it into, it shuffles and inserts into each box. This is an example grid. It's different every time. And so with I have 3 strategies that go along with my algorithm. 2 which take the bulk of the load, and in fact can generate thousands of valid Sudoku grids with just those 2 strategies. But every few thousand iterations it needs that 3rd. So, and I think that's pretty good. I'm going to start explaining what it does. It starts sorting row by column, row by column, row by column. And the amount, or the unsorted cells start shrinking like that. And so I've called it the shrinking square algorithm. So it goes through this row, and 3, 6, 1, 7, 2, and it's registering these numbers as it's going along. Uh-oh, found a 6. That's already a registered number. So what it does is it goes through the remaining cells in that box and tries to find one that is not sorted. If it's sorted, you might end up unsorting a previous row or column. But we'll get to that later. It's all part of the same strategy called box and adjacent cell swap. So anyways, this is just the box part. So it goes through, 4 is the very first integer it comes to, and that's unregistered, so it swaps and moves on. So it keeps doing that, and in this column, it reaches, it goes 7, 6, 8, and then 8. That's a registered number. We can't have that. However, this is in a row that's already been previously sorted. If we swap this 8 out with a 1, then we're effectively unsorting this row. As I was explaining before, don't worry, because there's actually a solution around this. So what it does is it looks only adjacent to itself. So this 4 and 2. Because if you swap with either of those, this row still stays sorted. It still contains 1 through 9 with no repeating values. 4 just happens to be the first value it came to, and it's done. It continues on. Later on in the algorithm of this example, in row 5, it goes 8, 4, 6, 3, 1, 7, 9. Doing great so far. 2, 7. Last value. 7. There's no 8. So the 8, 4, and 3 are already registered, so it can't swap out with that. So it has to look at this previous 7, and 9's already been sorted. You can't swap with that, even though it's already registered anyways. And then your only 2 values available are 5 and 6. 5 is the one that's unregistered. Swaps with that. And then real quick, 5, 1, 3, 6, 9, 8, 7, and 3. 8, 5, 9, 1 doesn't work. Those are already registered, so it comes back here. 3, and because these are sorted already, it can only swap with adjacent cells. So if 3 can swap with 6 or 4, 6 is already registered, swaps with the 4, done. Bada bing. Now, here's where the second strategy comes into play. This strategy is called preferred adjacent cell swap. And what it does is most of the time it just blindly swaps it. But if it does see a value that's unregistered, or a number that's unregistered, it will swap with that. So there's a preference on unregistered numbers. However, in this one, you'll see what happens. So it goes 5, 1, 4, 6, 9, 8, 7, 3, and it gets to the 4. 8, 5, 9, 1, can't swap with it. So it comes back to the very first occurrence of the number 4. 6 and 3 are already registered. That's why the box and adjacent cell swap failed. So what it does is just indiscriminately just starts swapping. 4 with the 6, so now there's 2 6s. 6 with the 5, now there's 2 5s. 5 with the 9, and then 9 with the 2. Stop! 2 is the unregistered number, so it stops right there. And with those two strategies, it can solve several thousand. However, once in a while, it gets stuck here because there's no more unique cells to swap with. Maybe a number is stuck somewhere in the woodworks that it can't get to. Maybe it's like an infinite loop. Either case, after 18 iterations, because there's a maximum of 18 swaps it can make. And what it does is allows the computer to say, you know what, just put this off to the side, go to the next row and column, sort those out, and then come back. And when it does go forward, that strategy is called the advance and backtrack sort. So it advances, sorts out the round column, which effectively pulls out the number needed, and then it backtracks, and then it's able to solve it. And with those 3 strategies, it can solve every single random generation of a Sudoku grid. And it does it perfectly every time. So I'm really excited about it. You can download this in my GitHub repository. I'll leave the link below. And also, please do comment and let me know what your strategy would be. How would you sort this algorithm? Do you think that there's a faster way? I'm sure that there is. I'd really love to know. Thanks a lot for watching. You have a good one.